Hi everyone. So today I'm going to talking about multitask represented learning for mixed integer linear programming. So to give you a background, mixed integer linear programming are used in a lot of real-world problems like path planning, scheduling, and network designs. And normally people use exact methods to solve smaller instance to optimality, and people use a heuristic method for harder instances to approximate the solutions. And when we're talking about ML-guided MILP solvings, there are a bunch of tasks that we can do for both exact methods and heuristic methods. And there is already a lot of great research in these different tasks. But in the ML-guided MILP solving, so we are stuck in a setting of distributional MILP solving. We need to use knowledge from previous days or previous instance to guide us to solve the future days or future instances. So that is it, we need to train a dedicated model from scratch for each MILP problem domains and ML-guided MILP tasks. So to address this problem, I introduced the first multitask learning framework for MILP problem solvings. So this pipeline includes a two-step training process. So first step, we train the network architecture with fixed output layers. So this we can ensure we learn effective MILP embeddings across different tasks. And second, we fine-tune only the task-specific layers. So this we can ensure our MILP embeddings has benefits from the different tasks without interfering the previous network architecture. So for the benchmark problems we are evaluating, we use combinatorial auction, minimum vertex cover, and maximum element set. And for the ML-guided tasks, we use backdoor, prediction search, and configurations. So let's look at the experiment results. We compare the default solver, Groby or Skip, the single task model, which is the SOTA in the previous paper, and our multitask model. So as you can see in the figure, our multitask model have achieved competitive performance within the distribution where the model is trained on. So looking at the blue line and orange line on the right graph, you can see the two lines are very competitive. But when we compare the model we trained directly on larger instance, talking about the generalization performance, we can see our model have much better performance when generalization on a larger instance size. So the orange line is much better than the blue line on the bottom graph. So to the future, we would like to build a foundation models for the MILP problem domains. Thank you.